I've been deconnected.
You're still connected.
Okay, I lost my. Okay. Good morning, everyone. So I'm Maxime Lombard. I'm a postdoc in Paris-Saclay working with Anaëlle Maury in our ERC project. And this morning I would like to show you a bit our work on the study of dust evolution in a protostellar collapse. That's the movie. So we know like planet formation form like the planets form in less than a few million years, which is a fast formation of planets. And we know like it starts from a molecular cloud. So locally we detect grains from nanometer to micrometer, and locally in this cloud you will have the formation of the young star and a disk gravitating around this young star. And in protoplanetary disk, we detect micrometer and millimeter grain size. So we have the dust growth to explain the formation of the millimeter grain. And then this grain will continue to collide and grow and with other physical processes to form the planet with a size, like the core of the planet will have the size around 10 to 4 kilometers. So we have to understand how we pass from nanometer to 10 to 4 kilometer in a few million years. And for that, we need to understand how the dust growth process is an efficient process in the planet formation, So to understand how this dust growth can be efficient, we need to perform a 3D simulation of evolution of protoplanetary disk, but also of a protostellar collapse to understand the formation of disk with all the physical processes. And in this simulation, we have two types of simulation. So for the disk, on the left side, we have simulation of disk, but also protostellar collapse, where they analyze the dynamic of gas and dust in one dimension, but being able to follow the evolution of the full dust size distribution. So for the disk, we have the known algorithm called dustpile, where we can follow the evolution of the dust size distribution with the dynamic in 1D. But now we have also the code called SHARC, developed by Hugo Lebris in Paris, which is able also to follow the evolution of the dust size in a 1D simulation of protostellar collapse. And on the other side, to do 3D simulation of protoplanetary disk, we can obviously use a phantom, of course. And also in the protostellar collapses, we have some 3D simulation, where in the both case, we can only use a single approximation for to follow the dust size evolution, but we have the 3D dynamics of gas and dust. So now what we need to understand and to fully understand the planet formation process, we need to be able to run 3D simulation of gas and dust and following the full dust size distribution. So it's still a challenge so far. And why is because of the modeling of the dust growth, which has been modeled by Marian Chmieloszewski at the beginning of the 20th century. So this nice physicist gave us this nightmare equation, which is it's called the coagulation equation. So it's to model the dust growth through a collision between the grains. And the unknown variable is the number density of particles per mass unit. So this variation during a small time is given by the difference of two terms. The first term is the gain term, which explains how to form a particle of mass m, so for instance, the orange particle during a small time, so through collision of smaller particles. And the loss term is explaining how the number of particles of mass m reduce due to collision with other particles in the system. So it's a nonlinear integral differential equation. So that's why it's a nightmare. And in general, so for astrophysics case, we cannot solve it analytically. So we need to solve this equation numerically. And in astrophysics, so we have the function k, So here in the function tail, which describes the physics of the collision between the collision of two grains. And in astrophysics, we use what we call the ballistic form of this function k, which writes like the cross section, the geometrical cross section of the two particles, so of the two grains, and their differential velocities. So why it's still a challenge to solve this equation in astrophysics domain? It's because we need to solve this equation efficiently and by following these two main requirements. Basically, we want to follow the evolution of dust size between 1 micrometer and 1 millimeter, what we observe in a protoplanetary disk, which represents 9 order of magnitude in mass, because we have the equation on the mass variable. And the main difficulty is like the function n, which is a continuous number distribution with the mass. We can only discretize this function n with a maximum of 20 mass bins. Why this number of 20? Is to be able to run the 3D simulation. So for instance, if you try to run a phantom with 100 or 200 mass bin or size bin, I guess you will have troubles to be able to run it. So this number of 20 is to be able to run the simulation and to treat the coagulation among other physical processes in the simulation. So from the start, so I did my PhD with Guillaume Leb. So Guillaume called me, hey, I have a PhD topic for you. Let's do it. Maybe I should have said no. So what I did is like I apply advanced numerical scheme called discontinuous Galerkin scheme to be able to solve efficiently the coagulation equation in its conservative form. So from the previous slide, we can write the coagulation equation in the conservative form because it's a mass conservation process. And when we know this equation, we can apply very robust numerical schemes such as finite volume scheme, and here the discontinuous Galerkin scheme. So the main idea of this mathematical framework is like before, such as different algorithms, they were approximating the continuous number density distribution by constant piecewise function. And now, thanks to this new method, we can approximate in each bin by polynomial. So we can keep a fixed number of bins, like 20 bins, and reach high accuracy by increasing the order of the polynomial for the approximation. So this is the main idea of this discontinuous Galerkin scheme, and which is adapted to solve and to rise the challenge. So I show you a benchmark of this new algorithm Koala. So thanks to some simple form of the collision kernel, we can have analytical solution of the coagulation equation for the additive kernel. So on the y-axis is the mass density distribution versus the mass in log scale. In black, we have the initial condition. So we start with a small grain. Then we let it evolve and we obtain the blue curve, the analytical solution where we have coagulation, we form large grain. In orange is the result obtained with dust phi when we use only 19 bins to discretize the non-order of magnitude of the mass range. So we see like dust phi is not very well adapted. And with Koala, when we approximate by linear function in each bin, so we can obtain a very good approximation of very good accuracy compared to the analytical solution. So Koala is adapted to treat polydispersed coagulation in a 3D simulation. Now I'll show you a first result we obtained in Paris. So first I have to apologize because I've been going to the dark side of numerical scheme by using a grid code. Phantom is not happy, of course. So we implemented Koala in the code Ramses to perform a protostellar collapse with a gas dust dynamic. And in this simulation, we used 40 bins. And we can follow the dust growth in each cell of the simulation. So this is a 3D visualization of the simulation of the gas density. And here I show the evolution of the dust size distribution in one cell. So in this one, for instance, starting from an MRN, and we see like we have evolution of the MRN due to coagulation. So I can show you a bit more detail of the result. So here is a 2D map from when the star created 0.2 solar mass. So this is the first row is with no growth, and the bottom row is with growth. So we see the difference between the APIC map. So APIC is the maximum size for the MRN distribution, and here is the peak of the distribution. So we see we have growth. And to give some result, like when we choose the 250 nanometer, which is the peak of the MRN where we cut, when we choose this bin, it represents 20% of the total dust mass. And after, when we we switch on the growth, it's now represent 12% of the total mass. And this is taken over a very large scale, like 4,000 AU from the central star. So to give you some idea. And we can also detail a bit more. So in this simulation, we have only coagulation and not fragmentation. So we have to analyze the physical result compared to some fragmentation velocity threshold. So basically in the simulation, the main source of collision of particles is due to the turbulence. So based on the Hormel model. So we can compare, we can evaluate the differential velocity from the Hormel model for the side at the peak of the distribution. And we can obtain this map, which is a plot. So differential velocity is plot versus the radius. And we can select the cells which didn't reach the fragmentation threshold, obtained for two types of grain, like silicate grain and isotopic grains. So, and then if we analyze the evolution of the size of the peak of the distribution in these cells, we obtain this kind of plot where we can try to fit a power law to understand the evolution. So the analysis is still in progress to have the result. So so far it was just coagulation. So but Koala is adapted and solve also the fragmentation equation, which has this form. So it's a similar expression than the coagulation equation. The difference is like we need to have to know the mass distribution of fragment, which is an input function. And what was missing in the literature is the conservative form I derived with colleagues, and which correspond like physically, or the second term in the expression can be physically linked to the mass transfer process, where after the collision of two particles, for instance, between a large and a small particle, a small part of the small particle will remain stick to the large one. So we have kind of sticking process inside the fragmentation process. So when we do the benchmark of Koala for one analytical solution for the fragmentation equation, we obtain the very good result when we discretize the mass range with 20 bins, which allow Koala to be adapted to solve the fragmentation equation in a 3D simulation. So far, we only have a spherical grain, which is not very realistic, of course. And so Koala will be well adapted to treat on the same time the fact that dust have a non-spherical shape and has a multi-component, multi-composition. So how to do that? It's simple. We just need to add more complexity into the coagulation equation. So yeah, let's do it. So for instance, we can follow the evolution of the composition of grain through coagulation. And all the modeling will be part of the sticking probability, which depend on the composition of the grains. And for that, to be able to have accurate modeling, we need to have the data from a lab experiment on the collision of grains of different composition. Then we can do the same for the shape of dust and extend the Shmushevsky equation to integrate the fact like to define an aggregate, we can define it by its mass and its porosity. So we can follow the number density distribution with two variables, this time the mass and the porosity. In the literature, we have some model to describe the mass porosity of the new form dust. And also, it's missing a bit of modeling to know this time for the fragmentation, what will be the mass and the porosity of fragment after a collision. So for that, we need also data from a lab experiment. When we know that, we can apply Koala and have a good result. And the working plan of this new project is to be able to have simulation with gas, dust dynamic, and the dust growth and fragmentation. We have colleagues which will study and bring a new realistic dust optical properties to be implemented in a radiative code transfer and obtain realistic synthetic observation in protostellar collapse, but also in a disk protoplanetary disk. And I leave you with my take-home message. So Koala is ready to fight with growth and fragmentation. Thank you.
We have questions. Thanks, Maxime. If you go back to your slide number 9, I'm not sure I understood what are the velocities that you show here, 20 meters per second and 3,300. Is this the velocities of the grains in the simulations or the velocity threshold for fragmentation?
The threshold for fragmentation is calculated with the breaking energy from the Hormel paper. Like you give the size of the monomer and the physical property of the grain, and you can obtain this velocity when you consider collision of grain of the same size.
I'm surprised because those values are very high compared to what is used in disks usually.
Yeah, so this is modeling and not taking from experiments, lab experiments. So yeah.
Okay, and last question. When is Koala coupled to Phantom?
Haha, it's working from yesterday. It's on the good way.
I guess the thing we would like to try is disk simulations with this. So do you see any limitations or problems? And like how much of a performance hit is it in Ramses compared to the regular Hydro?
So this was just the first simulation where I use constant piecewise approximation for the simulation. We use 40 bins to be accurate enough. And by doing this simulation, the executable time is just with a factor 2 compared to no growth.
Is there a time step constraint?
Yeah, it's like mainly the coagulation will work with the hydro time step. There is not too much subcycling. It will depend on the maybe more in the disk in this part where we will reach high density of gas and dust. So, but it's there is not too much subcycling, so it follows the hydro time step. So should be not bring too much troubles. Yes.
Yeah, nice talk. One question regarding the multi-component grains. So it's cool you're implementing that. What is your plan? The two components or the multiple components, is that going to be an homogeneous mixture, or do you plan to deal with coatings or?
So the equation cannot deal with the coating directly. It has to be modeled probably in the sticking probability.
Okay, so you would have some sort of an equivalent refractive index in the end to move towards stacking property.
Because so this equation just can follow the mass fraction of components.
And the same question regarding shapes.
Yeah.
You're going to deal with the gyration radius and porosity, or the exact shape depending on the collisional velocity and whether you collide fragments or individual particles?
So it has to be analyzed, but will be easier to follow the mass and porosity.
Yes.
So which seems to be the best combination of variables to follow the evolution.
So in the end, the effective particle is still a sphere.
Yes. No, it's not a sphere because now this kind of particle will be defined by the mass and its porosity.
Yes.
So you will follow the porosity of the particle. But so the fact to have the non-spherical shape will also be included in the kernel collision for the cross-section term, will depend on the porosity or the elongated or not shape. And but no, at the end, you will, if you can define this by the mass and the porosity, you will have a 2D function for the number density of this particle. So there will not be a spherical.
So we have to end the question session. Yeah.